Here, a structure question from October-November 2017, paper 22, question 6. A. State what is meant by an electric current. By definition, is the rate of flow of charge. So here is the formula of charge in terms of time. So when we have a variable in terms of time, we say it's a rate. Next question, B. A metal wire has length L and cross-sectional area A as shown in this picture. I is the current of the wire. N is the number of free electrons per unit volume in the wire. V is the average drift speed of a free electron, and E is the charge of an electron. I would like to add one more variable, N sub E, which is the number of free electrons or electrons. Question I. State in terms of A, cross-sectional area, this, E, the charge of an electron, L, the length of the wire, and N, the number of electrons per volume, an expression for the total charge of free electrons in the wire. To answer question I, I'm using these two equations. One states that the charge is equal to the number of free electrons times the charge of one electron, which is quantitative, 1.6 times 10 to the negative 19 coulombs. So that's why the answer for charge is coulombs, because you multiply the number of electrons by its charge. The second equation is this definition right here. N is the number of free electrons per unit of volume. So number of free electrons over volume. Now I'm going to rearrange this formula in terms of the number of electrons, Ne, which is the N times volume. Now I can answer this question because this question is asking to find an expression for the total charge of free electrons in terms of these values. So one thing that we can do here is this. My charge, or Q, is equal to my Ne is N times volume times E. So this is my Ne. So the shape of this wire is a cylindrical shape. So the volume of a cylinder is the area times the length or height. So I'm going to highlight this for you. The volume of this shape, which is cylinder, is the area times the length or height. In this case, L for the length. Okay, so now I'm going to substitute the equation for volume right here. So now is Q, the total charge is N times the volume is area times length times E. There what is left. So now I have the expression in terms of A, E, L, and N. So I complete this question. The second question is asking to use this result from I to show the current I is given by this equation. So I'm going to start with the answer from the question I. And I need to introduce the current. Now we know the current is the rate of charge So it will be charge over time. And I can rearrange this formula for charge, which is IT. Okay, now I'm going to marry these two equations. So which means that this NALE is equal to IT. Now I'm going to flip this, so IT is equal to NALE. Don't get confused here. I'm just shift position. Rearrange it for I is NALE over T. Now, L is length over time. This is speed or velocity. Velocity is length over time. Now, the final answer, current, is NAVE, which is exactly this equation right here that I need to demonstrate that I can be given by these variables. In this box here, we can write a remember type of clues. Number one, how do you remember that velocity or speed is length or distance over time? One way is think about miles per hour. So miles per hour can be written as miles. This per is a division and this is hour. So here we have length over time. So that's the way that you can remember. Another tip to remember this formula is I is equal navy. So just remember navy. When the charge is an electron, works really well. I, current, is equal navy. Question C. Is it still related to the same wire, but something else happened? Let me read for you. A metal wire in a circuit is damaged. The resistivity of the metal is unchanged, but the cross-sectional area of the wire is reduced over a length of 3 millimeters, as shown in this picture. The wire has diameter D at cross-section X and diameter 0.69 D, smaller, at cross-section Y. The current in a wire is 0.5 amps. Question CI is asking to find the ratio for the average drift speed of electrons at cross-section Y over the average drift speed at cross-section X. In other words, is asking the Vy over Vx. Let me start with the formula for current in a wire. So if I want to rearrange for V, so V is I over NAE. So then I can do a substitution, I over NAE for the section Y over I, the same formula, I over NAE for the section X. So the section Y is the damaged one and the section X is the one that is not damaged. When you see a wire that has changed shape, a couple things you need to know. Number one, the current flowing through the wire on different segments that is changing shape, current is the same always. If you had a third section here, the current also will be the same. Current will not change through a wire. Now, the second factor that is important is that the metal is unchanged, which means the resistivity is the same. So current and resistivity on both sections are the same. Another factor that is also the same is the number of electrons per volume. Even though the material has changed shape, cross-sectional area, but this ratio remains the same. So here we have the same number of electrons per volume. If you have a section, you have the number of electrons per volume. And if you have another section, this is one section, you have another section here, you find the same ratio, the same number of electrons per volume. Saying that the N on both segments are the same. So N on both sections and I on both sections are the same. Another one, the electrons is the same on both sections. Electrons will not change. Electrons are electron. So the electron in this segment and this segment are exactly the same. So what do you do when you have so many things that are the same? And as a fraction, we are going to cancel. So I with I, N with N, and E with E. And what is left? Just the cross-sectional area for each segment. So the next step, after cancel everything, what we have left here is 1 over AY, and this is 1 over AX. I have highlighted this step because the importance of understanding when we have a fraction over fraction, the way that you rearrange this is the fraction that is on the numerator remains the same, but the fraction on the denominator you flip. So then you have times the flip fraction, which instead of 1 over AX, you'll be just AX over 1. On the prior page, we talk about the cross-sectional area of a cylinder is circular. So the area, the formula for area will be the area of a circle, which is pi times diameter squared over 4. Okay, so now I'm going to make my substitution on this formula, which means that AX, the area, is pi d squared over 4 for the section X, and on the denominator is pi d squared over 4 on the section Y. Now, since pi over 4 is a common term on both equations, we can just go ahead and cancel, and what we have left is d squared on the numerator and d squared on the denominator. Okay, so continuing with this process. So d x, the diameter on the section X is d, just d. So I'm going to replace here with d squared, and the diameter on the section Y is 0.69 d. So it's 0.69 d, all this is square. So before I keep going with this, I'm going ahead and cancel d squared because this d is going to be square too. So d squared with d squared, and now I have 1 over 0.69 square. So 1 over 0.69 square is equal to 2.1. So this ratio is 2.1. Here is a side note about this result that I want to show you something. So my drift velocity on Y over drift velocity on X is equal to 2.1. So if I want to find the speed, the drift velocity on this section, will be 2.1 times the speed on X. What that means? The speed on Y is faster than the speed on X, and makes sense because as the cross-sectional area gets smaller, the speed increases. I want to make an analogy with the water hose, and this is the water flowing through the pipe, and you need to water your grass. So if you want to increase the speed of this water flow, usually you place our finger right here and you kind of make the section smaller. So what happens is the flow of water leaving the hose is going to go farther because it's going to speed it up. Very important note, narrow the wire, drift velocity increases. Question C, 2 I's. The main part of the wire with cross-sectional X has a resistance per unit length of 1.7 times 10 to the negative 2 ohms per meter. For the damaged length of the wire, calculate 1. The resistance per unit length. So this question provides the resistance per unit length for the section X, which is 1.7 times 10 to the negative 2, and is asking for the resistance per length for the damaged section. So here I'm going to start by separate the sections, X for the good wire and Y for the damaged wire. Resistance in terms of length and area of a wire is given by this formula, and I'm going to rearrange this formula in terms of R over L, which is, I'm moving L down here, and resistivity over area. Now I'm going to rearrange this equation for resistivity, which is rho L is equal R times A. Just do cross multiplication here. So then my resistivity is R over L times A. So now I move this guy down here. The head of this problem here states that the resistivity of the metal is unchanged, even though the cross-sectional area has reduced, but the resistivity is the same for both sections, which means that the resistivity for the section X is equal to the resistivity of section Y. So doing my substitution right here, so R over L on X times AX is equal to R over L on Y times AY. So this is the ratio that I'm looking for, the resistance over length for the damaged wire. So what I'm gonna do is I'm going to rearrange this formula one more time, and I'm gonna move this guy here on the first section of this equation, Y, right? And I will keep the second term of this equation as it is. Didn't move anything. Now I'm going to move this guy to the other side. Is multiplying, go dividing. So this is over AY. Another way that you can do this is divide both terms by AY to eliminate this AY. If you divide both terms, you are going to have the same result. Divide here by AY and divide this by AY, and you will just cancel all this, and you have R over LY, which is this one, times this over this. Now this is the question, where do I get this? Now do you remember that I highlighted this section right here? So I'm gonna pick up from here to show you something. So Vy over Vx is equal to Ax over Ay. And we know this is 2.1, which means that, that's the result, 2.1. So which means that Vy over Vx is equal to 2.1 and Ax over Ay is also equal to 2.1. Great, now I can keep going. So my Ax over Ay is 2.1. My R over L for the section X was given, which is 1.7 times 10 to the negative 2. Okay, so now I have the value of R over L that was given, Ax over Ay that we calculated prior, 2.1, and when I multiply both, I have a 3.6 times 10 to the negative 2 ohms per meter. So to answer this question, the resistance per unit length for the damaged section, which is Y, is 3.6 times 10 to the negative 2 ohms per meter. Now the second question related to the damaged section Y is to find the power dissipated or lost in that section. First, to calculate the power, we need a formula. The formula that I'm using here that is related to our system, current was provided, and is related to the resistance. So I'm using this formula here. P is equal I squared times R. On the question section C, the current was provided. The current in the wire is 0.5 amps. So we are using this value. The damage length is 3 millimeter. So I'm using the milli as a multiplier, which is 10 to the negative 3 meter. Another information that we need from this question is the resistance per unit length for the damaged section, which is 3.6 times 10 to the negative 2 ohms per meter, which is this fraction right here, resistance per length. So instead of having abbreviations for the formula format that I'm using here, I'm just kind of describe everything so you can see better. So once I have the damage length, which was provided in the problem, the resistance per unit length that we calculated on the previous problem, previous question. Now I'm going to calculate the resistance of the damaged section, which is the resistance per unit length that I have here times the damage length. Now the product of 3.6 times 10 to the negative 2 with 3 times 10 to the negative 3 is 1.08 times 10 to the minus 4 ohms. Why? Because this meter cancels with this meter. So the only unit that is left is ohms. Now I have the resistance of the damaged section in ohms. Now I can calculate the power dissipated in this damaged section. So P is 0.5 squared times 1.08 times 10 to the negative 4. So 0.5 squared times 1.08 to the negative 4 is 1, 2, 3, 4, 5, 2.7 times 10 to the negative 5. Last question, triple I. the diameter of the damaged length of the wire is further decreased. Assume that the current in the wire remains constant. State and explain qualitatively the change, if any, to the power dissipated in the damaged length of the wire. First, from this formula, we need to look at the relationship between resistance and the cross-sectional area. So resistance is inversely proportional to the cross-sectional area. Okay, so here say the diameter further decreased, so which means that the cross-sectional area is decreasing. So since the cross-sectional area decreases, so the resistance increases because both resistance and cross-sectional area are inversely proportional. Now I'm going to bring another equation in this picture. Is power is the current square times R. The problem states that the current remains the same, so current is the same. So this formula here, power will depend only on the resistance. Since the resistance increases, so power also increases. This question is pretty long, so before finalize this video, I just want to go through each page that I answer for you. So the first part of this question is just asking to find a expression that is related to the number of free electrons per volume, cross-sectional area of this wire, the length of the wire, and the charge of an electron. So to solve this, we just need to know how to handle pretty much those two equations. And also understand that the volume of a cylinder is the cross-sectional area times the length of the height. With manipulation of those three equations, we can easily find what the question is asking. Then moving forward to find the current of a wire in terms of the drift velocity of electrons. So now we just need to combine two formulas for charge, and the only thing that you need to know is how to convert the length over time into velocity, and then you get the formula they are asking. This page is all about the section that was damaged. So here is asking the ratio between the velocity of electron when compared with both sections. The normal one is the damaged one. So then we conclude that the speed of the electron in this section is about 2 times greater than the speed of electrons in this section here. Then the following question is asking to find the resistance over the length for the damaged section when the resistance over length of the good section was provided. And we have this, and also we have the relationship between both sections by the area. So that way I could manipulate with all this information to get the ratio the problem was asking, the resistance per unit length for the damaged section. In this second question is asking the power dissipated in the damaged wire. So was provided the current and also the length of the damaged wire. And this is the information from question 1. So with all these, we could calculate the resistance of the damaged section, which is this one, and use this information on this power formula and to find the power dissipated or lost as a heat in the damaged section. So the last question is related to a hypothetical scenario. If the diameter of the damaged wire keep getting smaller, so what would happen to the power? So here we have to answer using two formulas. One, the original formula for the resistance of a wire, considering that the resistance will increase with the decrease of the diameter. And then the second formula is formula that we used prior to calculate the power dissipated. And the information was given that the current is the same, but the resistance is increasing after our analysis here. And therefore, we can conclude the power will also increase. We're going to have more loss as heat in that damaged section if the diameter keep decreasing. The total mark for this entire question is 12 points.